Hello, beautiful people, and welcome to 7.6, which is all about writing and graphing exponential growth and decay functions. Our SWABAT is to graph exponential growth and decay functions. What a novel idea. Okay, let's go through our first little bit of information here for you. Linear versus exponential. So you have already graphed, and we've talked a lot about linear functions. Linear, look at the word in there, line. It should be a line when we graph it. New for most of us, though, is exponential, and exponentials will be a little bit more of a curve, and instead of just growing at a constant rate, it's going to grow either really, really quickly, so this is going up really sharply, or this is for growth, it will fall really fast. So see this big old drop from like 0 to 1? It's going to decay exponentially. That means really, really fast. So linear equations, which you've seen before, are of the form y equals 3x plus 2, some number times x plus possibly a constant. Things to notice here: as x gets bigger and bigger from left to right, or even smaller, y is going to have the same pattern for each and every number. So from here, what do I have to do to -4 to get to -1? Add 3. Add 3, add 3, add 3. So the difference for the y values, that's what we care about. What's happening with the y values is I'm adding, or I'm going to subtract by 3. Well, no, not every time, but some constant number. And then when I graph it, it's going to be a line. Because why? Because it's linear. And then also things that you might remember is this equation right here, y equals mx plus b. Y equals mx plus b. Contrary to that is exponential growth or decay. And this could be of the form, instead of 3 times x, 3 to the x. See what I did there? Not 3 times x, but 3 to the x. Exponential functions. Think about that. Exponent. Your variable is going to be an exponent for exponential functions. And over here, notice how we were adding, could have been subtracting by a constant. Instead, we could be doing times 3 times 3 times 3 times 3. Now this is kind of hard to see that it's times 3 as you go from here to here, even from here to here, but I can see it easily as I go from here to here. What times 2 gives me 6 multiplied by 3? 6 times 3 gives me 18. Sometimes I kind of will skip this, like the fractions, and look at the whole numbers because it's a little bit easier to see. And then I can go back and just double check to make sure, oh yeah, this is times 3. So when you have exponential functions, you are either going to multiply or divide. Now the thing with dividing is the same thing as multiplying by a fraction. So you're still doing the same thing. One thing to note is if you're multiplying by something, it's going to be exponential growth. And if you are dividing, or like multiplying by a half, then it's going to be exponential decay. Yeah. And then this is our general basic formula that we're going to be dealing with here. And then as you can see, it's going to grow up in a curve, or down, depending on if it's growth or decay. Can be neither. And I'll show you something about that a little bit later on. Okay, there's a little bit of info for you. Turn your page. And now we are at our first example, which is asking us, determine whether the rule or table represents a linear or exponential function. Is it linear or exponential? So in order to determine that, I'm going to look at it, and the x values just go 0, 1, 2, 3. That's fine. There's no jumps. It doesn't go 0, 1, 5, 9. It's all in order, which is great for us. So I'm going to look at this and determine, okay, well, what's happening from one to the next? Well, I could say that I'm adding 2, or I could say that I'm multiplying by 2. This can verify it for me. 4 to 8, well, adding 2 no longer works, but if I multiply by 2, I get it. If I multiply 8 times 2, I get it. I get the next term. Times 2 times 2 times 2. Therefore, this is, if it's multiplying, exponential. Okay, let's check the next one. That's all they wanted, exponential, linear. right here, I have two options. It could be plus 2 or it could be times 2. Now let's look. If I add 2 to this one, I get 6. 6 plus 2 gives me 8. That didn't work out. So therefore this is linear. Again, this works if I'm adding or subtracting. If I had done minus 2, minus 2, minus 2, minus 2. Why does that work? Because it's like saying plus negative 2, plus negative 2. For this one, it could have been times 1/2 or divided by 2 if it was something else. All right. Bueno. Let's look at this one. Letter C, is it exponential or is it linear? Well, you're going to look at the x. And the x is an exponent, so it's exponential. Exponential. Good. For the next one, I'm looking at the x, and the x has an exponent, but it's to the first power. This is actually just 3 times x. To the first power, no one needs the 1 because no one cares. This, therefore, is linear. If you notice that x, not an exponent, so it's linear. Letter E, the x is an exponent, so this is exponential. It's saying times 3, times 3, times 3, times 3. This is actually saying times 4, times 4, times 4, times 4. And if this was in a table, it'd be saying plus 3, plus 3, plus 3, plus 3. Took me a minute to think about that. Okay. Now, the next thing that we would like to do for this whole entire section is to, not the last thing though, is to evaluate each function for the given value. Evaluate each function for the given value. So, let's read this. This is function notation. This is saying the function, with regards to x, is equal to 15 times 0.4 to the x. I want to evaluate that when x equals 3. So I want to put for the function, when I plug in 3, is equal to 15 times 0.4 to the third power. So, and this is the function when I plug in 3, not the f times 3. Different notation. So this is 15 times 0.4, 0.4, 0.4, 3 times. This is, I'm doing this in case you don't have a calculator. Sometimes you don't. So 4 times 4 times 4, I do know that is 64. And then there's 1, 2, 3 numbers after the decimal point, so 1, 2, 3 times. You can check me on a calculator, I won't be offended. And then 15 times 0.064 is equal to 0.96. I actually did that one in a calculator, I didn't know it in my head. And that is my answer. But remember, this is saying the function when I plug in 3 is equal to 0.96. Do I need to divide by 3? I do not, because this is just function notation. Okay, let's try another one just like the other one. And if you want to, I would not mind if you did this on your own. But this is equal to y instead of the function f of x, doesn't matter, same thing for s, is equal to 3 times 1.5 to the x, which is to the negative 2. I'd be stressed out. Well, I probably wouldn't be stressed out because I don't stress out like some people. But 1.5 as a fraction is 1.5. As an improper fraction, multiply and add, is 3 over 2. Cool. And you probably would get to use a baby calculator for this, but let's pretend like you don't have that. So this is 3 over 2 to the negative 2. Not stressed out still. This is 3 times 3 to the negative 2 because I know my properties of exponents. And 2 to the negative 2. I'm distributing that. So this is 3. Now what happens? This is negative up top, so I move it down and now it's 3 squared. This, negative on the bottom, I move it up and it becomes positive 2 squared. Still not stressed out. This is 3 times 2 squared is 4. 3 squared is 9. What if I put this over 1? I can cross cancel and get a 1 here. No, I would not get a 1 there. 3 goes into 3 one time. 3 goes into 9 3 times. Misfits, check your math. And so y is equal to 4 over 3. Voila. Now, what if I hated that? I probably would let you use a calculator. You'd get the same thing, but you'd probably get 1.33333333333. If you did this on your own and you got 1.33333333333, or if you got 1 and 1/3, I'm fine with that too. Okay. Shall we do a little tiny bit of graphing? Even if you said no, I'm still going to do it. If you're feeling like, I feel risky with that last example, don't worry about it. I got you. We're going to do the same thing for these problems right here as well. So we're going to just practice that just a smidge more. Graph the function. Graph the function. Y equals 2 times 3 to the x. Y equals 3 times 2 to the x. Now, every time you're not going to get this because you're going to make your own, but I'm going to want you to make an XY table. And every time I want you to have 1, 2, 3, 4, 5 points. And I want you to always use these 5 points. -2, -1, 0, 1, 2. Why do you need so many? Well, because you haven't graphed these as often as you graphed the other ones before. So trust me and join me now. First one, where do I want to do this at? I probably want to do it up here-ish. So when x equals -2, y equals 2 times 3 to the -2. Okay, order of operations, do not multiply that first. I will fire you. And then I'll put this over 1. Oh no, I can't fire you. And then I'm going to flip it 1 over 3 squared. 2 times 1 over 9 is just 2 over 9. So remember, this was 3 to the -2. Negative exponents have to go down. So I moved it down to the bottom and had 3 squared, which is just 1/9. So I get 2 over 9. Let's do another one. What about when x equals whatever the next number is, -1? Then I get y equals 2 times 3 to the -1. 3 to the -1, if I put this over 1 as a fraction, 1/3. So I get 2 over 3. 0. If you're thinking it should be 1, you are forgetting that 2 up in front. This is 3 to the 0. 2, what's 3 to the 0? I hope you said 1. And then 2 times 1 is 2. So for that one I get 2. Add a space over there, not a problem. I'm going to continue right here. 2 times 3 to the first power is just 2 times 3, so that's 6. I got one more to go. Are you seeing a pattern? You should. You should be doing times 3 times 3 times 3 times 3 should be 18. This is telling me what you're multiplying by each time. But in case for those of you that don't believe me, I'm going to do this part in green just to show, yeah, I told you so. 3 times 2 squared. 2 times 9 is, just like I said, 18. You should see a pattern here, so use that to our advantage. Now, if you're looking at those numbers and then you're looking at our graph, you're thinking, oh my gosh, you didn't even make it big enough. I'm trying to show you, you don't need to make a ginormous graph that goes all the way to 18. No, don't do it. Instead, change the scale. You don't need to change this. This is your x values, and your x just goes from -2 to +2. So -2, -1, 0, 1, 2. That's fine. But I have 1, 2, 3, 4, 5 lines, and I need to go up to 18. 5 lines, and I need to go up to 18. So what should I go by to make sure that this fits? How about 4? 4, 8. I'll be so embarrassed if it doesn't fit. 16 and 20. Whew, made it. Okay, so -2. Now that 2/9, super close to 0. -1, super close to 0. 0, well here's 4, so 2 has to be right in the middle. And then 1, here's 4, 8, right between 4 and 8 would be the number 6. And then here's 2, there's 4, 8, 12, 16, all the way up to 18. It should curve like this. We want this curve. It will never ever cross this axis right here. This is called an asymptote. It's a line that your graph will approach as you go far out to infinity, but it will not actually cross. and then you're going to connect your graph. Goes up forever, super close, but doesn't actually cross it. There you go. I love that graph. I did well that time. Okay, let's try one more. This would be exponential what? Exponential growth or exponential decay? What would you call this one? Well, as I look at it from left to right, it's growing up really quickly. So this would be growth. Okay, they didn't ask me, but I'm sharing it anyways. Part B. Well, let's graph it. Let's plot these points like we did for the last one. So my first one is x equals -2. And so I get y is equal to -2 times 1/2 to the -2. Those negative exponents, beautiful people, they just flip it. This is the same. Negative exponents mean reciprocal. So this is the same as saying 2 over 1 squared. It's the same as -2 times 2 squared. Remember, you have to do exponents first, so this is 2 times 4, which gives me -8. -8. And then for x equals -1, it looks like if I'm thinking this is right, I'm thinking I probably need to go to 1/2 of whatever this number is. But let's double check and see. In my mind, I should just have to multiply this by 1/2 to get the next number. So what's half of -8? -4. Don't believe me? Just watch. So I get y is equal to -2 times 1/2 to the -1. Reciprocal. This is like saying 2 to the first power. It's -2 times 2, -4. Yes, it is. So what's half of -4? If I'm right, this should be -2. I'm going to show you probably just one more time. So x to the 0. -2 times 1/2 to the 0. What's 1/2 to the 0? Anything to the 0 power, Miss Fitzgerald, is 1. So that's -2. I was right. Look at that. It happens every now and again. So this is my factor, my decay or growth factor. Neither in this case because this is negative. So I just have to multiply each thing by 1/2. Times 1/2, I get -4. Half of -4, -2. What's half of -2? -1. What's 1/2 times -1? -1/2. Don't believe me? You can always plug it in to check. I'm just going to check the 2 because that seems to be where I'm getting the most out. This is 1/4 because 1/2 times 1/2 is 1/4. Put this over 1, -2 over 1. Oh, I just messed that up. I just wrote the same thing twice. -2 over 4 equals, ding, 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 1/2. Beautiful. Now, let's talk about graphing this. I have 1, 2, 3, 4, 5 lines, and I think I'm going to go by 2s because that just seems to make sense. I'll make this -2, -4, -6, -8, -10, although nobody cares, and this is 1 and 2. -1 and -2. Okay, so here's -2, -8. Remember, all of my graphs have to be on graph paper. I know you don't get these graphs because I didn't give them to you to do your homework on, but so -1 right between 0 and 2. You do have to do all these on graph paper. This is getting closer to 0 there. All right. Okay, connect, connect, connect. And this will eventually just go down forever, and then we will approach. Now, not all of my curves actually look this pretty decent here. Sometimes it takes me a minute to get back into the practice of them. So if you have never graphed these before, don't stress out. Like when I was actually practicing some of these graphs, this is how my first one looked. It's a little zigzaggy. The main thing is, though, you don't want it to look like you connect the dots here. You're actually getting a little bit past that. I don't want it to be zigzaggy and staccato. I want it to kind of just curve and be smooth throughout. Just like that. And let me give you a tip, life hack. If you mess up and your curve looks like a little too zigzaggy, then what I like to do is just go over it with a thicker marker mostly because it just hides some of my mistakes. Don't be too obvious with it though. Alright, that is your lesson for today. Thank you so much for joining me, and have a great day. Bye-bye.